What is the pressure on the oceans of Europa? How do you measure the day length on a gas giant? And what would the total solar eclipse look like from the moon? All this and more in this week's Question Show. Welcome to the Question Show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Kenneth Walbom. Does anyone know how the pressure in the ocean on Europa compares to the pressure in the ocean on Earth? So it's believed that Europa, one of Jupiter's moons, has this thick icy shell, and then underneath that is an ocean of liquid water. And we don't know how thick the ice shell is, and we don't know how big the ocean of water is. So I'm going to give you some numbers, but they're probably wrong, and we're going to need to wait for a couple of missions to actually get to Europa to give us an answer. So we're waiting on the Europa Clipper, which launches this year, and we're waiting on the European Space Agency's JUICE mission, which has already launched, and both are going to arrive at Europa in the early 2030s, and then they're going to attempt to measure the depth of the ice, try to work out the gravity field of Europa to figure out where is that layer between the ice and the water and then the solid core. So just keep that as a caveat. Future Fraser will be able to give you these numbers. Current Fraser cannot. But let's assume that the ice sheet is about 20 kilometers thick. And it's, that's sort of a lower end. It could be a lot thicker than that. And so if you are at the ocean on Europa, right at that level between the ice sheet and the water sheet, you have 20 kilometers of ice, of water, pushing down on you. And so you would think, well, that just means that it's like I'm under 20 kilometers of water. But the gravity on Europa is 1/7 the gravity that we experience on Earth. So you have to make some calculations. So if you were to make those calculations, you would get 26 megapascals of force pushing down on you from the ice that's above your head. And that is equivalent to you being under the water on Earth by about 2.7 kilometers. So assuming that the ice is 20 kilometers thick, which it probably isn't, then it's the equivalent of you being about 2.7 kilometers down, which is like a lot, but it's feasible for us to be able to do. Now, the actual liquid ocean on Europa is thought to be about 100 to 200 kilometers deep. So once again, 1/7 the gravity. So you're looking at about 130 to 260 megapascals. And that is equivalent to you being about 13 to 26 kilometers deep under the ocean on Earth, which is impossible because our oceans don't go that deep. And so when you're thinking about some kind of robotic explorer that's going to need to explore the oceans on Europa, at the very beginning, it's going to need to be able to handle the equivalent of being 2.7 kilometers under the ocean on Earth. But at its maximum level, if it's going to try to get down to the bottom of the ocean and examine the black smokers, it's going to have to be much stronger than anything that is routinely deployed here on Earth. So it is a challenge to even get this kind of technology to Europa, an even bigger challenge to have it survive. But it's not like 1,000 times the amount of Earth. It's feasible, just difficult. I don't know if you noticed, but there was a Star Trek planet name that appeared above my shoulder on that first question. And this is a way for you to vote, for you to tell us what you thought was the best question of the week. And last week, we got a 4-way tie. So nobody could really decide what they thought was the best question. So congrats to Dreamcast Knight, to Dot3Dog, to Cosmic Collisions, and Nomad77CA. So thanks for everybody who voted. Now, the way you vote is we're going to put up a different Star Trek planet name each time that I go into another question, and then you can just write down in the comments down below which one you like the best, and then I'll gather them up, and hopefully we'll have one winner next week, but who knows? All right. And also we'll put them into the show notes and we'll put them into the chapter markers. So you should be able to see what all of the planet names are. All right. Don't forget to vote. Randall Hensler. Shouldn't they build a new iteration of the James Webb telescope that can fit in SpaceX's new Super Heavy rocket? So when James Webb launched, it launched inside an Ariane 5 rocket. And this has sort of a industry standard fairing size of about 5 meters across. And so the entire telescope was designed to fold down and fit inside that 5-meter fairing. And then when it reached orbit, it unfolded itself. The primary mirror is 6.5 meters. So that's bigger than the fairing size of the Ariane 5 rocket. But really the big thing is the tennis court sized sun shield that it uses to keep itself cool from the sunlight that's coming. So Starship has a fairing size that is 9 meters across. So almost twice as wide as the Ariane 5 and much longer. And so the question is like, how big of a telescope could you fit inside the SpaceX Starship? Now, there's sort of two approaches to go down this path. One is don't get fancy, right? Just use that 9-meter size to just put a big telescope, a simple telescope, into the 9-meter fairing. When you look at a lot of the telescopes that are out there, things like the Hubble Space Telescope, things like Spitzer or Herschel, they look like tubes, right? They're just a tube with a primary mirror and secondary mirror, and they fit inside the spacecraft that was designed to launch them. Hubble came from the space shuttle, while Herschel and Spitzer fit within a rocket fairing. And so, you couldn't do a 9-meter telescope, you could do an 8-meter telescope, I think, inside Starship. And already that would be the most powerful telescope that humanity has ever launched. It would be incredible. And it would be about the size of sort of the smallest possible iteration of the LUVOIR telescope. Right now the plan is to make the Habitable Worlds Observatory telescope to be 6.5 meters like the James Webb Space Telescope. I wouldn't be surprised if SpaceX pulls this off, makes Starship work, even in a disposable basis. Then it's worth designing a telescope that is like the Hubble Space Telescope, but bigger and fits within a 9-meter fairing just straight up. Don't get fancy, just a tube inside a tube, and you put it into space. Now you've got an 8-meter telescope like Hubble. When Hubble's 2.6 meters, now it's 8 meters. It's going to have, probably double the capability of James Webb, but also be very specific. It's going to be able to do ultraviolet, infrared, and visible light. It's going to have a coronagraph. It's going to allow you to see potentially Earth-sized worlds orbiting around sun-like stars. But what if you did get fancy, right? What if you wanted to follow the James Webb route and you wanted to build a folding telescope that you could then put into a rocket like Starship and then launch it? Well, then it could be much bigger. Like you could probably get a telescope that is definitely more than 10 meters, maybe 20 meters across. Maybe you could get even bigger than that if you fold it up nicely. But I don't think that's probably going to be the route, because building James Webb was a big challenge in sort of making all of the parts work right, shaving off the weight of every single component of the telescope. The budget just went up and up and up, went up to $10 billion, vastly more than anyone was ever planning to make. And I don't think that people want to make that mistake again. They don't want to deliver a telescope that is going to be over budget and delayed. They want to build a telescope and want to deliver it on budget, on time. And so I wouldn't be surprised if the next generation big space telescope is following more like Hubble, more like Nancy Grace Roman. It's a tube inside a tube. But the idea that I really like is on-orbit construction. So instead of just launching one launch that has your entire telescope inside of it, what if you launch one component at a time, like we did with the International Space Station? Launch the main bus, it's got robotic arms. Then you launch the primary mirror and it assembles the primary mirror with its robotic arms. The telescope kind of builds itself. Or you have astronauts that fly to it. And so there's a lot of options. What something like Starship gets you is it's going to be relatively low cost to launch a large amount of mass with a large fairing. And if it works, which we still don't know if it's going to work right now, it'll be a game changer. But even the worst possible iteration, where you have to destroy both Starship and the Super Heavy with every launch, that gives amazing capacity for new telescopes. Trenton 3779. How do they measure day length or rotational speed on gas planets since they don't have a solid surface? Yeah, you're exactly right. And this is kind of a mushy question because when you look at planets like, say, Jupiter, the speed that the planet appears to be rotating on its equator is different than the speed it appears to be rotating at its poles by several minutes. And so you've got to ask yourself, like, which part of Jupiter are you talking about? Because you get this differential wind speeds that are going on the planet. And so parts of the planet are turning faster than other parts. So that's one way to ask the question. And so if you want to say, like, how long does it take for the Great Red Spot to go around the planet? It's roughly 9 hours and 50 minutes. And you could have that as one way to measure the rotation speed. But that's just one part. Think about, say, the core. Maybe there's more of a solid core inside Jupiter. How long does that take? And how do you know? Because you can't see the surface features the way you can on Mars or Mercury. And the way they do that is they measure the magnetic field that is coming out of Jupiter. It's incredibly strong, very obvious, and there are these sort of magnetic field features that rotate with the planet. And so they look at the magnetic field of Jupiter and they measure for that magnetic field feature to return back to the same location. And that gives them a number. Again, roughly 9 hours and 50 minutes. But Saturn is a trickier one. And in fact, it has defied any attempt to measure its rotation speed until just a couple of years ago. If you asked a planetary scientist 5 years ago, what is the rotation speed of Saturn? They'd be like, I don't know. It's like kind of 10 hours and 30 minutes, but we don't really know for sure. And so you go to that same process. Like, you can't tell from the cloud speeds because the clouds are moving at different rates. You actually can't tell from the magnetic field because it doesn't have this really powerful, precise magnetic field in the same way that Jupiter does. So any attempts to measure the rotation speed based on the magnetic field just didn't work. And so only in the last couple of years, scientists figured out a really clever trick, which was they didn't look at the planet itself, but they looked at the rings. And there are these ripples, these gravitational ripples that are caused in the rings. They're like standing waves. And they were able to find those waves in Cassini data, and they were able to map how long it takes for those standing waves to come around the planet. And they found that it takes 10 hours, 33 minutes, and 38 seconds. And so it wasn't until 2019 that we finally learned what is the day length on Saturn. And so you can take that idea and just take it to any other planet. You're looking for features in the atmosphere to be turning. You're looking for the magnetic field, and then you're looking for potentially rings, other things like that, to try and give you some sense of how quickly the planet is turning. The other thing that you can do is that there's an oblateness to all the planets. So, for example, Jupiter and Saturn both turn so quickly that they're flattened blobs. They are sort of wider at their equators than they are. The distance across the equator is more than the distance from pole to pole. But this thing is just turning, then it doesn't really give you an answer of how long it's happened. It's just how long is this oblate spheroid turning? But you can have interactions with other planets and things like that. And so the spheroid gets a little bit of a torque as well. And suddenly now it's more like a football that is turning, and you can get a sense. But it's been really tricky to do that, not very accurate. This method, looking at the rings of Saturn, was like the most accurate way and give them the answer they were looking for. Alex, what would a total solar eclipse look like from the moon? How much time would totality last? I'm glad you asked. Now, I just saw the total solar eclipse from Dallas for the first time. Like, I tried to see it in 2017, but there was clouds, and so I didn't get a chance to see the full eclipse. But this time, 2024, in Dallas, perfectly clear skies, I saw it. I saw the corona, big prominence down on the lower right-hand side. It was amazing. It was perfect. Sorry, what was I talking about again? Oh, right, your question. So From our perspective on Earth, we see the sun and then we see the moon taking this chunk out of the sun. But from space, what you see is the shadow of the moon falling onto the Earth and moving across the planet. And fortunately, there were a whole bunch of spacecraft that were watching this event. So there was the astronauts on board the International Space Station. They were flying or orbiting around the Earth. And so they orbited over the eclipse area, and they can actually see, there's a video where you can see them talking about the eclipse as they're flying overhead. One of the GOES satellites, these are weather satellites, was able to watch the entire eclipse. And so you can see the shadow, this time-lapse image of the shadow come in from the bottom corner, up through the Earth. It sort of moved through North America, out through the top of Canada, and then back out into space. But your question was, what would it look like from the moon? And it would look roughly the same as that GOES image. But in fact, we did get some images of the solar eclipse from the moon. Now, there aren't any spacecraft on the surface of the moon that were able to take a picture, but NASA's Lunar Reconnaissance Orbiter was in orbit around the moon. I'm sure they had this planned very carefully. They were able to look back, look at the Earth, and take a picture of the eclipse shadow moving across the Earth. So how long would totality last? The length of the entire eclipse track. You would see the shadow fall and then move all the way across the planet and then come off the top again. The total length of the eclipse sort of depends on sort of where the shadow falls on the planet and how much planet it has to pass through. But it's hours. It's going to take hours as it moves along from one limb of planet Earth across the planet and then out the other limb. Sashil Narayan, do you have any suggestions for a backyard telescope hobbyist? You've asked a question that really sort of begins a rabbit hole. I mean, how deep do you want to go down the rabbit hole of being a backyard telescope hobbyist? You can buy a very inexpensive telescope for a couple $100, or you can spend tens of thousands of dollars more on building the perfect backyard telescope. So I'm not going to go into all of the various options, but I can give sort of the quick answer that is best for most people, and that is to buy a Dobsonian. Most people who want to get a telescope and want to be able to see the night sky, they tend to live in cities, and they really are most excited to be able to see the planets. You want to see the rings of Saturn. You want to see the moons of Jupiter. You want to see the Great Red Spot. You want to see the polar ice caps on Mars. You want to be able to see the amazing craters on the surface of the moon. You want to get a solar filter and be able to see sunspots and prominences on the sun. And you can do all that with a Dobsonian telescope. And that's not a specific supplier. That is a type of telescope. They're very simple to use. They're very simply built, but they're very powerful. And they really give you the best bang for the buck. You can buy like an 8-inch Dobsonian for less than $500, which sounds like a lot of money, but an 8-inch telescope is a lot of telescope. You can see the moons of Saturn, the moons of Uranus. You can see just really precise objects in space with a telescope that is 8 inches. And yet they're very simple to use. You see a thing in the sky, you just point your telescope at it, you look through the finder's scope, and then you are looking at that object. You can set it up quickly, invite your friends over to take a look at the telescope, show them Saturn's rings for the first time. It's a very satisfying thing. And the nice thing about a Dobsonian as well is they work really well in dark skies as well. So if you live in a light polluted city, you're not going to be able to see fainter nebulae and galaxies and things like that. But you can take that telescope, you can go to a place that doesn't have a lot of light pollution, and suddenly you can see all kinds of other objects. You can see comets. So that is my number one recommendation for like most people. If you just want to get a telescope, get a Dobsonian. Now, if that $500 for a Dobsonian is too expensive for you, and it is for a lot of people, then you can actually build these things yourself. You can go on to, say, Alibaba or other like wholesale places. You can buy the mirrors, which are just the main primary mirror. You can buy the secondary mirror. You can buy a few other mounts and bits and pieces, and you can put a telescope together like that if you're handy for less than $100. So, if you have the money, buy a Dobsonian. If you don't have the money, build a Dobsonian. And that is like for 95%. Like if you don't have a telescope, the answer is buy a Dobsonian. If you have a telescope and then you want to get into other things like taking pictures of the sky with a telescope, if you want to get into astrophotography, then that's a whole other subject matter. There's a lot more branching options, which I can talk about if people want to hear about that. I know you want to hear about that. All right, well, let's get into it. So let's say you want to take that next step and you want to take some actual pictures of the night sky. There's kind of two main paths to go. The way that's relatively inexpensive is to buy a tracking mount for a camera. So if you already have a digital camera, then it's really about the tripod. You can buy these tracking mounts. They're relatively inexpensive, a couple $100s. You put your camera on top. You've already got a nice fancy DSLR camera. It's got probably different kinds of lenses, wide area lenses, narrow lenses, and you can use that to take pictures of the night sky. And it's kind of amazing what you can get done with that for a couple $100s. The other route, and this is the one that I do not recommend unless you are like absolutely sure and committed, and it's going to cost you thousands and thousands of dollars, is you build a telescope rig. So you're going to need a really nice mount, a really good telescope, a camera system, tracking software, a bunch of other stuff. It's going to cost you thousands. And there's like a third option that's come out in the last couple of years, which I do like for some people. And these are these automated, robotic, smart telescopes. There's the Stellina, there's the Eviscope, there's the Dwarf 2. There's a bunch of these now. And they take a lot of the complexity out of this process. It's like, it's got a telescope built in. It's got the software to run it. It's got the mount. It's all baked in together. Camera system. And all you have to do is take these things, put them down. They figure out where they are on Earth. They take a couple of pictures of the night sky. They figure out what their orientation is. And then you can just pick objects that you want to see from an app on your phone. And then it will go ahead and find those objects and start taking pictures of them. And you are actually taking pictures of galaxies or nebulae or things like that. And some of them have light pollution filters, so you can take pictures when you're in the middle of a city. They're amazing. And, they always say like the best camera to use is the one that you have on you. And so like often we mostly take pictures with our phones. And the nice thing about these robotic telescopes, these automated telescopes, is they're very easy to use. They work very dependably. You're going to use them. The downside is the pictures aren't as good as what you could get if you built a telescope with all the separate parts and set it up, because you have a lot more customization. And these things are expensive. I mean, on the low end, I think you can get them for like about $1,000, but for the much better ones, they are on the order of $4,000. And so you've got to have a lot of money if you want to be able to buy one of those things, but they are very easy to use. They take okay pictures and you will use them a lot. So hopefully. And the last advice, everyone's going to be screaming at me. So yeah, if you want to just figure out whether or not observational astronomy, amateur astronomy is a thing for you, the best place to start is with a pair of binoculars, astronomical binoculars. They're about $100, and you're looking for ones like Celestron makes a great pair, the Skymaster series. You can take those and they're a completely different and very wonderful experience. You can see the planets. You can just barely make out, say, Saturn's rings or Jupiter's moons in these binoculars. You can see comets, fainter deep sky objects. You can see the moon looks amazing, and you can take them on trips with you. So a bunch of options there. Start with binoculars, go to a Dobsonian, decide if you want to take pictures, decide if you want to go the DSLR route with a tracking mount, or an automated telescope, or you want to build a more complicated rig. But it's that complicated rig that gets you into the $10,000, $20,000 to $100,000 range. Hope that helps. Good luck. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who's already subscribed, and welcome to our recent newcomers: Scott Donnelly, Mark Woods, Linda Jerka, Anne Burnside, Lek Croft, Jeremy Waldrop, Michael Muhe, Patrick Eakin, Charles Shopson, Michael Meyer, and Oguchi Nagwacha. Join the club at patreon.com/universetoday. Potato Biden, who are the real science gatekeepers? There are no science gatekeepers. The scientific community is a vast group of human beings around the world in hundreds of different countries who work for different organizations, people who work at universities, people who work at governments, at research agencies, space agencies like NASA. I mean, they're all different people, and they will then do their various research work that is funded in different ways. In some cases, they're funded by wealthy patrons. In some cases, they're funded by governments. They're funded by universities. They're funded by corporate interests. So they're funded in many different ways. And generally, the scientists will do their work and they will publish the results of their work in journals. And the journals are owned by different publishing groups. So there are no individual gatekeepers that are looking over all of this material and deciding this gets shown, that gets shown, this doesn't get shown, whatever. I mean, it is just, you're kind of like saying like, who are the gatekeepers of, I don't know, like the economy? Like it's just, there's so many players that are all moving at the same time. I think there are incentives that tend to push scientists into different directions. You know, there's this idea of publish or perish, that the economy of scientists is to do a lot of science. And the way you've shown that you've done a lot of science is that you publish your results in peer-reviewed journals. The more prestigious the journal, the better. And by doing that, you then can sort of interact with your colleagues and look over each other's work and go from there. And then the scientists are the ones who are, I guess, they are peer reviewing your work. And so if you write a paper and it gets published in a journal, then you are placing a flag and you're saying, I have discovered a thing. I've discovered something. I believe that there is phosphine in the atmosphere of Venus, for example. And that could be an indication that there is life on Venus. And then other scientists are going to take your work and they're going to look through it carefully, step by step, and then they're going to try and find any mistake that you might have made. And then they're going to respond. They're going to write their own paper that references your work and says, here's all the ways that person said this, but I think it's wrong. And here's my results. And so now you've got two competing scientific theories that are both published in papers. And then more scientists are going to try to figure out all of the bits and pieces and break these theories. And whatever can survive the longest is the one that is widely considered to be the best theory of the time. So, like, who is the real science gatekeepers? Nature. The laws of the universe are the true gatekeepers. All science is trying to do is describe reality. And if what you're describing is like not correct, does not accurately reflect reality itself, then it's just a matter of time before reality rears its head and shows you the truth. And hopefully, as people are looking over your work and peer reviewing, they can get to reality as fast as possible. But I think anyone who thinks that there's like a way to gatekeep reality, I don't understand how that's even possible. Like, reality, as I said, has a way of revealing itself, and those are the laws. Andrew M., what will you do differently to prepare for your next eclipse? So, I mean, everyone I talk to having seen this eclipse, they're like, I want to see another one. What's it going to take? And unfortunately, the upcoming eclipses aren't going to be as easy to see as this one was. I mean, this one just went right through Mexico, the United States, and Canada. It went through huge cities. It was on land for most of its journey. And so you could just pick where you want to go depending on how good the weather is. For the upcoming eclipse, it's a lot trickier. You can be in Iceland on a little part just outside Reykjavik in Iceland, or you can be in that little part of Spain and Portugal. And so it's going to be a huge concentration of people into those two areas. The one in North Africa is going to be kind of tricky because it's going to go just up into the Mediterranean Ocean and skim the top of Africa a couple of times. The Australian one looks great. And, you know, you can kind of go anywhere along the eclipse path in Australia. But I guess there's a few places where you'd want to go, or New Zealand, which apparently people tell me is a real place. So this one's tricky. I mean, if you're going to try to go see the next eclipse, you're going to go to the places that everybody is going to try to go and see. And it's going to be a very different story. It's going to be a huge concentration of humanity into the few places where you'll be able to see this eclipse. And they're going to be kind of hard to get to. So I don't know whether I'm going to try to go and see the next couple of eclipses. It's just, it's going to be a lot more complicated than just hopping on an airplane, visiting my wife's family and watching an eclipse. So yeah, I don't know what the plan is. But I think it's always the same. Every time you try to see an eclipse, as I said in the last show, you treat this like a heist. You don't treat this like a vacation. You are trying to maximize your chances of seeing the eclipse. You've got to go to the places where you're likely to have the best weather. You've got to make sure that you've got ground transportation on the day of the eclipse so you can get to a place where you're able to see it. And you have to stay flexible the entire time. And so I would do that. I think this time around, like if I saw, when I do see another one, I probably will try to take pictures. Like after you've seen it with your eyes, it is worth it to try capturing the moment because every eclipse is different. I was listening to an interview with Fred Espenak, who's known as Mr. Eclipse. He works for NASA, and we rely on his data to know when the eclipses are happening, what parts are going to be seen by totality. He runs all these great simulations. And he says that he can just look at a picture of an eclipse and he knows which one it was because the shape of the corona, the placement of prominences on the eclipse are different. And so each one is unique. Now I want to see them all again. Anyway, I don't know. It's tricky. Dougal, thoughts on phone apps with sky overlay? I've tried a few of these phone apps and I'm not a gigantic fan. And maybe that's because I know too much, which is that I've learned my constellations. So I can go outside under dark skies, I can look up and I can orient myself. I know if it's in the summertime, I'm looking at certain constellations. If it's in the wintertime, there's different constellations. And those phone overlays, like they work. But I don't really feel like people learn anything from them. I don't know. It's like you take the phone, you hold it up, it shows you what the object is in the sky or what the star is or what the constellation is, but it doesn't stick in your brain in the same way. And there's a group of people who's watching this right now who learned your constellations the hard way, which is that you went out with a small telescope or binoculars night after night and you learned which star was what and how to find Hercules and how to find the Big Dipper and how to path from one star to another. And you were able to find Andromeda, which was really tricky. And bit by bit, the sky turns from just, boy, there's so many stars to, oh, there's Gemini. Oh, there's Leo, right? And that process is really valuable. And if you're going to use that phone app to teach you that constellation and you're going to drill it into your brain and you're going to go outside and you're going to confirm, oh, what's that? Oh, right. That's Leo again. It looks like a backwards question mark with a triangle behind it. Then if you use that, then it's great. It tells you what the thing is and then you memorize it and you go outside and you memorize it again. Great. And eventually you don't need the phone app. And I think that's the goal is you don't want to have the phone app. You want to be able to go outside and look up into the sky and feel at home. Feel like this is a map of the universe that you recognize, that you're comfortable with, that is very familiar to you. And that's the place you want to get to. So whatever method you use to get there, fantastic. Use a phone, use a book, but get there because it's worth it. Christopher Jacobson. How will Japan keep astronauts from bringing dust into their Artemis pressurized rover? It seems dangerous to be out working and sleeping with all that dust in the habitat. So this question is a follow-on from the news that we announced at Space Bites this week, where the Japanese Space Agency is going to be building a pressurized rover for an upcoming Artemis mission, probably Artemis 7. And this is designed to keep astronauts safe and secure in a pressurized environment on the moon. It's like a spacecraft with wheels that drives around on the moon for 30 days. So it's going to have the atmosphere for 30 days, be able to keep the astronauts alive, but in shirt sleeves and not have to wear a spacesuit like they did with the moon buggy they went with the Apollo mission. But you're exactly right that the lunar regolith is a gigantic problem. And it's a problem to just the rover itself out there on the surface of the moon. As the rover is going to be driving around, this tiny glass-like regolith is going to get into everything, all of the mechanical parts, and cause wear and tear on the rover. What is the solution? Go slow, try to minimize the amount of this regolith that gets kicked up and gets into the mechanics of this. Seal as much of it off as possible so that there's very few places that this stuff can get into. But the question you're asking is, well, what happens to the astronauts? If the astronauts are going to get out of the rover, roam around on the surface of the moon, and then come back into the rover, they're going to track this regolith inside the rover, and then potentially they're going to breathe it. It causes irritation of the lungs, maybe something more dangerous down the road. We definitely want to avoid that. So there's a couple of ideas for that. One is that NASA was testing out this idea with a previous iteration of their rover, which would have the suits, the lunar excursion suits would be on the outside of the rover. They'd sort of be bolted onto the outside of the rover. And then the astronauts would climb into the suits from inside the rover and then detach and then walk around on the surface of the moon. And then it was time to come back into the rover. They would push their backs up against the side of the rover, open up a portal, and then pull themselves back out into the rover. And so at no point do the suits go from outside the rover to inside the rover. They always remain outside. I think that's probably the solution that they're going to have to go with. And so you can kind of imagine as the rover is crawling around on the surface of the moon, it's going to have these multiple spacesuits sort of as if they're glued on the back of the rover. So this problem is partially solved, but there's also a lot of other technology that NASA and other agencies are working on right now to try and deal with this problem. And it's probably going to be some kind of electrostatic field. So at NASA, they are testing out with one of the upcoming Intuitive Machines launches, they're testing out a material designed to repel lunar dust with electromagnetism. And so like we know that this dust is charged, like static electricity charged. And so if you run a current along a surface where this material might fall down onto, you should be able to repel it and it's going to slough down. So I think you're going to have avoidance where you just try to minimize the amount of this regolith that gets into the rover. You're going to have mitigation where you are going to try to sort of minimize the amount that can actually adhere to any surfaces. And then you're going to have cleanup where they're going to be out there with sponges cleaning up this regolith to try to get rid of it so that it doesn't cause a hazard inside the spacecraft. It's a big problem though. Probably one of the biggest fully unsolved problems in space exploration on the moon right now. You Tubans, what did that gamma ray burst do to Earth? So, I mean, we see a lot of gamma ray bursts, but the one that I think you're talking about was the one that happened in 2022. It was very powerful, about 2 billion light years away. And it was so powerful. Remember, 2 billion light years away. But it was so powerful that it actually caused ripples in the Earth's ionosphere that were detectable. And so, the ionosphere is this one of the layers around the Earth, and it actually rippled from this gamma ray burst striking the Earth. Now, this was account of it being a very powerful gamma ray burst, but these things are a big problem. And in fact, astronomers aren't still 100% sure what causes them. We know that one type of gamma ray burst is caused by colliding neutron stars. And that was the kilonova event that we saw just a couple of years ago. And that matches some of the observations of some of these gamma ray bursts. You get these two neutron stars that are orbiting one another and they merge and you get this tremendous release of energy. And specifically, you get these outflow jets that go along the poles of the detonation. And if one of those is oriented towards the Earth, then it can strike the planet. But there's another kind of gamma ray burst, and astronomers are still working out exactly what their cause is, but it seems pretty likely that it is the core collapse of an extremely massive star. So think about the kinds of stars that are in the Large Magellanic Cloud, the ones that have dozens, if not more than 100 times the mass of the sun. When one of those dies, it is a catastrophic event. And it could be something that's a little more complicated, like maybe has like a binary companion, and that helps whip up these really powerful jets. And these are the ones that can be billions of light years away and still have a noticeable effect. And a gamma ray burst, like if it's pointed at the Earth and it is half a galaxy away, like if it's on the other side of the galaxy, it can still cause tremendous damage to planet Earth. It can weaken the ozone layer. And having less of an ozone layer is a big problem for life down on Earth. Now you're getting a lot more radiation from space. And so it's believed that these gamma ray bursts, if they happen close and struck Earth, they could have been the cause of mass extinctions in the past. Now, the good news is that we don't know of any potential stars that could cause gamma ray bursts in our vicinity, but they can affect you from such a great distance that they could be halfway across the galaxy. They could be in Andromeda and still have an effect on Earth. All right, those are all the questions that we got this week. Thank you everyone who asked questions in the YouTube comments, but also thank you everyone who joined me for the live show. We record this show live every Monday at 5 p.m. Pacific time, right here on the YouTube channel. You should see the event for the next one, and you're going to want to click the button that reminds you that it's going to happen. 5 p.m. Pacific time. The show is twice the length than what you're watching here, so I think you'll have a really good time. Come join the chat. Chat with the other people who are watching the show as well. It's a really good time. All right. I am going to recommend another small YouTube channel, but first I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Dennis Alberti, Dougie Stewart, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Mark Anstis, Modso, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. So thank you everybody who has been recommending small YouTube channels to me. This has been great. I've found a ton of new channels that I hadn't even seen before. And it's a really tricky time to be on YouTube right now, to be starting a channel. At the same time, you're in the midst of all of this AI nonsense. And if you don't have a lot of subscribers and yet you're telling good information, how do people know that you're legit versus the people who aren't legit? And the only way that we can do this right now that I can imagine is word of mouth, which doesn't seem very effective, but we're going to do our part. So this week I want to direct you to a channel called Cosmos Elementary. And I cannot believe they've only got about 6,000 subscribers at the time that I'm recording this. They've done tons of really interesting videos. We've got stuff about the horizons of the universe. How do you colonize the galaxy? Myths and misconceptions about the speed of light. And look, I'd never seen this channel before, and yet I watch it and they're really good. So check out Cosmos Elementary. So please keep those channel recommendations coming. People who have less than 10,000 subscribers who are doing a good, accurate job of teaching us about space and astronomy and other sciences as well, if we run out of the space and astronomy ones. All right, we will see you next week.